This is problem 9D3 from chapter 15, and this problem will conclude section 15.4. In problem 93, discs A and B have a mass 15 kilograms and 10 kilograms respectively. If they are sliding on a smooth horizontal plane with the velocities shown, determine their speeds just after impact. The coefficient of restitution between them is 0.8. So they also show you on the diagram here that this is the line of impact. So this is no problem with oblique impact because we have velocity in the horizontal direction and our line of impact at an angle to that. And they show you this is a 3, 4, 5 triangle. So the first thing that I would like to do is to break the velocities that they give us up into components which are parallel and perpendicular to the line of impact. And we could do the impulse momentum equation without breaking the velocities up, but remember for equation 1511 for the coefficient of restitution, these are the components along the line of impact, so we will have to break the velocity up into components in order to use equation 1511. Okay, so I'm going to copy down the diagram that they gave me for this problem. So unfortunately, they already called this the y direction and this the x direction. So the line of impact that they showed me here, I'm going to call this x prime, and perpendicular to that will be my y prime direction. So I'm going to have to use x prime and y prime components since they already called this x and y. This is a 3, 4, 5 triangle, and perpendicular to the line of impact, that would be my plane of contact, so that's in the y prime direction. I have A going this way with a velocity of 10 meters per second, and B going this way with a velocity of 8 meters per second. That's all I'm going to do with my picture, but you can refer to the one in the book for more detail. This is problem 93. And mass A is equal to 15 kilograms. Mass B is equal to 10 kilograms. The coefficient of restitution is 0.8. In this problem, there is no friction. Okay, so first I'm going to focus on breaking down my velocity vectors into components. So VA1 is equal to 10 in the negative x direction. So let's call this VA1 x, and that's equal to negative 10. And using the triangle that they give me over here, if this is x prime, this is y prime, that is a 3, 4, 5 triangle. Let's call this angle here theta. Okay, but if that angle is theta, I can also draw the 3, 4, 5 triangle with this side being 3 and this side being 5, and then I have a right angle here, and this is 4. And I can use this for breaking the 10 and the 8 down into components. So if I have my vector 10 that's in the negative x prime direction, that would be proportional to 5. So to get the components there, that would be VA x prime 1 and VA y prime 1, and this should have been VA x 1. So the x prime component, that's this way. So to get that, that would be the negative 10 times 3 divided by 5. 10 times 3 divided by 5. And if your velocity initially is in the negative x direction, you'd have a negative x prime component. So that's going to be negative. Maybe I should draw this. So you have 10 going this way, so that's this, and this, and you have a positive y prime component. So this is 10 times this side is 4, so 4 divided by 5. This is -6, and this is 8. Then we have v, b, x, 1, which is equal to 8. So that's going in the positive x direction, so this is 8. So I would have a negative y prime component and a positive x prime component. So I have vbx prime 1 and vby prime 1. The y prime is negative, the x prime is positive, and the x prime component is proportional to 3 if 8 is proportional to 5. So this is 8 times 3 divided by 5. The y prime component is proportional to 4 when 8 is proportional to 5. So this is 8 times 4 over 5. And this is equal to 4.8. This is equal to -6.4. Okay, so now that I did that, I can use my impulse momentum relationship and my coefficient of restitution formula. So now do the coefficient of restitution equation and impulse momentum for x and for y. Okay, and it doesn't really matter what order you do these in. With the coefficient of restitution, this is along the line of impact, so that equation becomes along the line of impact. This is my line of impact here, so those are the x prime components. So this is v b x prime 2 minus v a x prime 2 over v a x prime 1 minus v b x prime 1. Okay, so we're going to start there, and my coefficient of restitution is 0.8. So I have 0.8 is equal to, I don't know the final velocity, so I have to leave that as vbx prime 2 minus vax prime 2 divided by vax prime 1. That's -6. Remember, you need to include the signs in this formula. And vbx prime 1 is 4.8. The denominator is -10.8. And if I multiply both sides by -10.8, -10.8 times 0.8 gives me -8.64. And that leaves me with, oh boy, I didn't leave myself much room there, minus vax prime 2. And this is equation 1. Okay, now I want to skip ahead and do impulse momentum in the y direction next, or in the x prime and the y prime directions. Because if I look in the y prime direction, remember that your forces when the objects collide are going to be the normal force that A exerts on B and the normal force that B exerts on A. These forces are in the x prime direction. So if this is your system, the impulse in the y prime direction is 0. So remember, the impulse momentum relationship is a vector equation. And so the momentum that I have in the y prime direction before is the momentum that I have in the y prime direction afterward. And in the y prime direction also, you can look at the two objects separately. So if I do the system for, I don't know whether this is A or B, but I guess it would be B. Oops, that one's going this way. And this one is A. Then for just B, there you go. For just B, the impulse in the y direction is 0. And for just A, the impulse in the y prime direction is 0. So we can say M, B, V, B, y prime, B4, plus the impulse, which is equal to 0 in the y prime direction, is equal to MB plus V, B, y prime 2. The mass doesn't change. And we can do the same thing for puck A. So no impulse in the y direction, if you look at each puck individually, means that their velocities in the y prime direction cannot change. Okay, so VBY prime 2 would be the same as whatever VBY prime 1 is. VBY prime 1 is negative 6.4, and VAY prime 1 is 8. So those are the velocities in the y prime direction afterwards. Now, like I mentioned before, you don't have to use the x prime and the y prime for the impulse momentum relationship, but it sure makes it a lot easier because in the y prime direction, the velocities do not change. Okay, so finally, we have to do impulse momentum in the x prime direction. In the x prime direction, if I looked at puck A on its own or puck B on its own, I would have impulse. But if I look at the system of the two together, the impulse in the x prime direction is 0 for the system as a whole. So that means I take the initial momentum for my two objects and add them together. So that's VA, this is in the x prime direction, so VA x prime 1 plus MB VB x prime 1. So that's the initial momentum for the system of the two pucks in the x prime direction. The impulse is equal to 0. The final momentum is MA VA x prime 2 plus MB VB x prime 2. I can figure out what I have on the left-hand side. Puck A has a mass of 15 kilograms. VA x prime 1 is negative 6. Mass B is 10. VB x prime 1 is 4.8. Is equal to MA is 15 times VA x prime 2, which is unknown. MB is 10. VB x prime 2 is also unknown, but these are the same two unknowns that I have in equation 1. This on the left-hand side is negative 90 plus 48. What I want to do on the right-hand side is to get either VA x prime 2 or VB x prime 2 without a term in front. So I'm going to divide by 15 so that this is just VA x prime 2, because this is how I like to solve my two equations and two unknowns. So if I divide by 15, 10 divided by 15 is 2/3. This is VB x prime 2, and then I have to divide this side by 15 as well. This is going to give me equation 2. Negative 90 plus 48 divided by 15 is negative 2.8. This is equal to VA x prime 2 plus 2/3 VB x prime 2. This is equation 2. So now I have equation 1 and equation 2, and because I divided both sides by 15, if I take equation 1 and add it to equation 2, VA x prime 2 will disappear. So I'm going to add 1 and 2 together. Let me just come down here and do that. So I have equation 1, let's write that as negative 8.64 is equal to VB x prime 2 minus VA x prime 2. That's what I have up here. Now equation 2 is negative 2.8 is equal to VA x prime 2 plus 2/3 VB x prime 2. If I add those together, I have negative 8.64 minus 2.8, which gives me negative 11.44. Then the VAX prime 2 minus VAX prime 2 gives me 0. And I have 1 VBX prime 2 plus 2/3 VBX prime 2. That gives me 5/3 VBX prime 2. Okay, so now I can take this and solve it for VBX prime 2, which would be negative 11.44 times 3 divided by 5. That gives me negative 6.864. This is the x prime component of the velocity. That should be in meters per second. And then I need VA x prime 2, which I can get from using equation 1. Using equation 1, I take VBX prime 2, and if I bring the VAX prime 2 over to this side and the negative 8.64 over to this side, I get negative 6.864 plus 8.64. That gives me 1.776. Okay, so now I have my components for the velocity. I have the x prime components here. So here are my x prime components. And then here I have my y prime components. I was asked to find the final speeds. Now I could use the components to find the angle that each puck goes off at by taking the inverse tangent of y prime over x prime. So I don't need to do that, but I could if I needed to. So to find the final speeds, I would have VA2 is equal to x prime component for VA is 1.776 squared. Y prime component is 8. This gives me 8.19 meters per second. And then for VB2, I have it's negative 6.864, but we're squaring it, so it doesn't matter that it's negative, plus the y prime component, which is negative 6.4, but again, we're squaring it, so that's not going to matter. And this gives us 9.38 meters per second. So here's our final answer. And that concludes 1593.